Thank you for your interest in DARPA and DARPA DSO. My name's Mike Fiddy, and I'm going to give you a brief introduction to our office. As many of you know, DARPA was founded in 1958 in the wake of the surprise of Sputnik. It will celebrate its 60th anniversary next year, and its mission continues to create and prevent strategic surprise. DSO, the Defense Sciences Office, is referred to as DARPA's DARPA, creating opportunity from scientific discovery, investing in and accelerating promising breakthroughs and opportunities in a wide range of scientific disciplines. The very broad portfolio of DSO is driven by the interests of the program managers. DSO is one of 6 offices. There are 4 technology offices, as you can see here: biological, microsystems, strategic, and tactical. And there's also the Information Innovation Office, I2O. Brief descriptions of each and their priorities are given. Being DARPA's DARPA, DSO considers itself a foundational office supporting all of these other 5 offices. Many transitions of new advances in science and technology from DSO are to these other offices. This is a quick snapshot of the focus areas in DSO, broadly divided into mathematics, modeling, physical systems, human-machine systems, and social systems. For any new program or funded project, we think about implementing the Hellmeyer Catechism. This catechism asks the important questions shown here. Hellmeyer, by the way, is a former DARPA director. The questions are to be very succinct and clear with no jargon. What is it we're trying to do? How is it done now? What's new about our approach? If we succeed, what difference will it make? How long will it take? Will it transition to the DoD? And how much will it cost? Characteristics of a DARPA program are listed here. We're looking for revolutionary ideas that impact national security. The ideas, as I mentioned, are articulated to the director by the office program managers and their interests. The projects are the important entity, project-centric and not investigator-centric, and multi-year portfolios are typical to encourage diverse teams and build new communities to address new challenging problems. Program managers actively manage and get involved in the programs. And these programs often start very quickly and may end quite abruptly. Having an ongoing program does not imply there's an ongoing investment in that topic. Old problems may be revisited if there's a compelling reason, if some new technological breakthrough looks likely, or that great ideas could emerge. But there is no interest in funding programs, projects that are just extensions of ongoing work or incremental in nature. And we look for strong commitment and persistence in performance and a willingness to take on these challenging problems. Here you see the current program managers in DSO. These slides, by the way, will be made available if you need to review them or follow up with any of the program managers here. Thank you for your attention.
This is Susan Sheehan from DARPA's Contracts Management Office. Today I will be discussing the BAA process for the Nascent Light Matter Interactions, BAA. The most important advice that I can give is to read the BAA. The BAA contains meaningful words such as must, shall, and should. You should highlight these words in the BAA and be sure to address the requirements in your proposal. Teaming under this BAA is strongly encouraged. Collaborative efforts and teaming are addressed in the BAA at Section 8B. Your proposal will contain technical and administrative sections. The mandatory templates for the sections are referenced in BAA Section 4B2. Doing well in the technical section of your proposal could lead to a selectable determination. Volume 1 of your proposal will constitute the technical and management proposal volumes. BAA attachments 3 and 4 contain the templates for Volume 1. Volume 2 of the proposal will be your cost proposal. The template for the cost proposal is found at BAA Attachment 5. And finally, Proposal Volume 3 will address admin and national policy requirements, and the template for this volume is found at BAA Attachment 6. Proposal preparation and submission instructions are detailed in the BAA and its attachments. You should follow these instructions closely. Detailed proposals are requested for phases 1 and 2. A rough order of magnitude proposal is requested for phase 3. Prior to the completion of phase 2, at approximately month 24, DARPA intends to request updated technical and cost proposals for phase 3 per specifications and guidance provided by DARPA. Participation in the competition for phase 3 is optional and will be limited to successful phase 2 performers. Any and all questions regarding the BAA should be emailed to nlm@darpa.mil. Frequently asked questions, including those from today, will be available on the DARPA DSO Opportunities website, identified in Section 8A of the BAA. You should check the website often as it is kept current. Funding instruments to be awarded against the BAA will be procurement contracts, grants, cooperative agreements, and other transactions. Abstracts in advance of proposals are strongly encouraged. This is addressed in BAA Section 4. See the mandatory abstract template as referenced in BAA Section 4B1. You must assert rights to all technical data and computer software generated, developed, and/or delivered to which the government will receive less than unlimited rights in your proposal. This is addressed in BAA Section 6B4. The assertions will apply to prime, contractor, and subcontractors. You must use the defined basis of assertion and rights category and justify the basis of assertion in your proposal. Proposals submitted against the BAA will be evaluated in accordance with the evaluation criteria identified in the BAA in Section 5. The criteria in descending order of importance are overall scientific and technical merit, potential contribution and relevance to the DARPA mission, and cost realism. DARPA reserves the right to select for award all, one, some, or none of the proposals received. DARPA does anticipate making multiple awards. There is no common statement of work, so proposals will be evaluated on individual merit and relevance as the proposal relates to the stated research goals and objectives of the BAA. And as a reminder, read the BAA.
I want to introduce you to this new program, Nascent Light Matter Interactions, or NLM. My name is Mike Fiddy. The goal of this program is to develop systematic approaches to the design of structured materials that change how we control electromagnetic waves. Now, some definitions. Nascent here means emerging, just coming into existence, at the beginning of displaying signs of potential. By light, in this BAA, I mean all electromagnetic waves. the NLM program is interested in approaches from UV to microwave. And by structured materials in the goal, I mean engineered structures that could include resonators, single resonator, multiple resonators, 2D, 2.5D, 3D engineered materials. And by control, specifically of electromagnetic waves, I mean anything like deflecting, focusing, frequency mixing, nonlinear effects, non-reciprocal effects, electromagnetic forces, absorbing, reflecting, any phenomenon that involves electromagnetic waves that can be managed by matter. What does the program expect? Well, recent developments in our understanding of light-matter interactions suggest we might be at a turning point in our ability to control electromagnetic waves more effectively. I cite here, for example, the knowledge we've gained through metamaterials over the use of resonance and shape, energy transport mechanisms, the role of near-field interactions and coupling, regulating density of states, dispersion engineering, and the increasing role of quantum and electromagnetic wave-induced forces in material structures that affect the electromagnetic response. So in this program, we will identify and develop new and emerging opportunities that advance how we control electromagnetic waves. We're looking for visionary ideas that point to new directions that provide significant extensions in our present ability to manage light-matter interactions. The outcomes from the program will be a deeper understanding of these interactions, a more systematic approach to manipulating, managing, creating electromagnetic waves, and the focus of these efforts and this new way of thinking towards addressing some important, fundamental and challenging DoD problems. Why now, and what are the opportunities? We're looking for a comprehensive approach for light-matter interaction descriptions and models that builds on but transcends the approaches we're familiar with today. And I cite recent advances like resonant cavity enhanced phenomena, breaking of Lorentz reciprocity, the role of gain symmetry, the appreciation of the role of epsilon near zero materials, advances in non-reciprocal structures, new approaches to defining the photonic density of states, new models emerging for nonlinear behavior and non-scattering structures, the use of optimization methods to design structures for wavefront control, and the increasingly interesting convergence of optical, nano, and mechanical phenomena that are leading to new properties at the nanoscale and opportunities for new methods for assembling structures. These are just examples that together in combinations may lead to new ideas that allow us to leapfrog over where we are today in exploiting light-matter interactions. So what kind of new phenomena may become or are becoming important? Are there more comprehensive ways of describing these interactions? What do we think are missing in our models today? Are they comprehensive enough to include material properties, quantum effects, radiation pressure, whatever is necessary to completely describe the phenomenon we're interested in? And can we pull this together to address challenge problems and hard application goals? For example, can we identify building blocks, elemental building blocks that go beyond our meta-atom circuit theory-based models and incorporate more complex behaviors, maybe nonlinear responses, for example, And can we predict those desired properties from models based on these building blocks? And can we use these models to form the basis of a rational and complete design strategy? And in other words, address the inverse problem, where we can specify a material characteristic we want and then design the physical engineered structure that behaves in that way. Equally important, can we do all of this in a way that these building blocks are able to be made, assembled, fabricated to take what we're trying to do here from just theory and simulations into the real world? Example phenomena which may be ripe for this approach and that teams might like to focus on are listed here, but proposers are encouraged to put forward alternatives that they may be thinking about that could impact the state of art in different areas. I list here extreme nonlinearities. Can we transcend the way we think about nonlinear responses today, essentially as perturbations of material properties which are necessarily weak? Much has been done making use of engineered structures to enhance local fields in order to boost nonlinear responses. But can we get beyond that? Can we get beyond a weak perturbation model in order to improve parametric phenomena, tunable structures, frequency conversion? Much has been written recently on unidirectional materials, many applications for these, non-reciprocal phenomena, time frequency engineering, new means for energy transfer between coupled systems. Density of states engineering could lead to new meta sources, engineered materials for emitters, control of energy and emissivity in a lot of applications ranging from turbines to chips. And then material structures which can manage high intensity electromagnetic waves, deflect waves, concentrate waves, perhaps provide new mechanisms for energy harvesting or power or momentum transfer of structures. These are just examples, but we're looking for new approaches, new models, which address these or other phenomena involving electromagnetic wave matter interaction. So the NLM approach is looking for proposals which contain the following important list of items. We're looking for an approach which provides a new method for characterizing matter, light matter interactions. And this new method must be useful in a predictive way and a parametric way and provide a scalable design tool. We want to see approaches which allow structure to be mapped to function and function to be mapped to structure. We want to understand in the proposals what are the range of materials and physical structures of interest and that could be characterized, and the range of electromagnetic interactions that are predicted. And those proposals need to quantify the structures that can be predicted and then the range of interactions that can be characterized. And the approach should be generalizable. Although initially the proposed approach may only be valid for a small subset of materials and a few light matter interactions, proposers need to show a path for generalizing the approach to broader classes of materials and broader or even completely general interactions with light. And then on top of this, a focused application or two needs to be proposed, that the light matter interaction model and the predictive tool, the design tool, can be used to advance the state of the art in one or more of these focused application areas. So phase one of the program will last 18 months and be concerned with identifying the approach to the nascent light matter interaction problem of interest. And in phase one, a predictive theoretical model will be developed, and the model's potential for accomplishing the NLM goals to exceed the state of the art in a phenomena will be demonstrated. A systematic approach derived from that model is expected to allow materials to be designed that have prescribed properties. So we're looking for the model, and the model to then be able to be used as a design tool. It may involve extracting building blocks, primitives, which, if so, need to be purposefully extracted and demonstrated as elements that enhance our understanding, provide better design tools, and provide a means to extend the characteristics of the phenomena, the state of the art, into new realms. These building blocks and devices and approaches need to then be tied to the chosen focus areas and applications. In phase two, which will last 12 months, all performers need to demonstrate that their approach can dramatically advance the state of the art in the chosen technical area, demonstrate the approach is scalable and robust, and provide a specific proof of concept challenge that will be executed in phase two. And while the proposal should include example proof of concept challenges, there will be a workshop held towards the end of phase one with government stakeholders who will help tune those challenge problems to ensure that a transition to DoD needs is guaranteed. The offerers should propose specific proof of concept challenge metrics that might be completed in phase two, and that this is enough to demonstrate that their predictive model and design strategies are effective. Towards the end of phase two, challenge problems for phase three will be defined, again after soliciting input and feedback from government stakeholders. Phase three will be 18 months long and will involve completing DARPA challenge problems that derive from that phase two stakeholders workshop. And our hope is that in phase three, there will be teams pursuing 3 or 4 quite different applications. The milestones for phase 1, 2 and 3 are cited here. In the first 6 months, we expect to see the predictive model developed, and at 12 months, the working design tool developed, with some preliminary simulations and experiments validating, depicting how it works and its likelihood of success. And then towards the end of phase one, the program review and stakeholder workshop will evaluate the progress made. Phase two is 12 months long. By month 24 into the program, performers should be able to verify performance metrics and demonstrate that they're on the path to verifying these metrics and demonstrating proof of concept operation of the associated design tools. Prior to the completion of phase two, at approximately this time, month 24, we intend to request updated technical and cost proposals for phase three. Guidance will be provided on these updates at a challenge workshop held at 25 months. This stakeholder workshop will consider the phase two progress so far and the opportunities that present themselves to establish clear superiority of new engineered materials over existing technologies. The evaluation of these Phase 3 proposals will be based on evaluation criteria that will be specified in these Phase 3 proposal requests, and the Phase 3 proposal evaluations will be conducted through a scientific and technical review process. The criteria for evaluation will be consistent with the criteria in this solicitation. Phase 3 will last for 18 months, and there'll be challenge milestones at 36-month, 42-month and 48-month from the beginning of the program to determine whether we're on track with the milestones that are specified. This last slide shows the program timeline. You see Phase 1, Phase 2 and Phase 3 shown. The blue diamonds indicate when stakeholder workshops will take place. In Phase 1, the first workshop will review Phase 2 proof of concept ideas and metrics appropriate to the team's technical focus areas. In Phase 2, the stakeholder workshop will occur around the time of the request for proposals for Phase 3 and will provide guidance on the goals and the milestones of the challenge problems to be executed in Phase 3. Thanks for your attention.